Okay, so we're going to continue on in Module 6. So in our learning plan here, you're going to notice that we're going to be working out of the handout here for Chapter 6. So it's kind of nice. It goes along with Module 6. And then we have the guided notes for the frames and the machines that we're going to be working on this evening. So if you want to print those off, go right ahead. But this is going to be what we're going to be working through. Turn off my video too, and I'm going to minimize this. Thank you. So I have this already printed out underneath my camera, and I'll kind of go back and forth. I do have the handout for Chapter 6 printed off, but the section that we're going to be looking at in that Chapter 6 handout starts on page 119. And it's going to be the section talking about frames and machines. Now, they go through, this is, I always encourage you to read the sections, whether it's in the ebook or the handouts that I provide you. I encourage you to do that, but I kind of hit the highlights, if you would, with the information in the guided notes here that is going to be, most pertinent to what we're going to be working on. So at the beginning here, a frame is going to be a rigid structure. So what you want to put in here is the word frame. So we're going to be looking first at frames. So a frame is a rigid structure that's designed to support external loads. They are similar to trusses, but the forces can be applied. But forces can be applied mid-span of a member. So if you recall, for trusses, all of the loads had to be at the joints, and that was where the members in the truss would be connected. Okay, we couldn't put a force like in the middle of one of those members. But here on a frame, this is the main difference. We can apply forces mid-span, and that is totally fine. So that's really the major difference between a truss structure and a frame structure. Okay, we will be solving for reactions at the supports of the entire whole frame, and then we'll be looking at the internal pin connections if and when there are present. Now, machines, on the other hand, are designed to transmit loads. Okay. So, and forces rather than to support them. So a machine, in basically your physics classes, you study simple machines like pulleys and levers. Those are designed to transmit loads. And yeah, they have an element of support maybe in them, but their main purpose is to usually help us gain what we call a mechanical advantage. Okay. So we'll be looking at examples of each of these in the second part of Module 6. Now, when we look at frame and machine problems, how are we going to solve those? Just like with trusses, we kind of go through a process. So the first thing we're going to do is we're going to draw our free body diagram as a whole together frame, okay? Just like we did for trusses, we showed the truss all together, okay? And then it says here, don't forget your convention, because we will be using our convention to identify positive and negative directed forces and moments. And then we're going to determine the reactions at the supports when we have that whole frame together, okay? Now, sometimes we might not be able to solve for all of the unknown supports, but that's okay. We're going to proceed anyway. I'll kind of show you that, and then we can always come back and fill in, okay? And again, that'll make a little bit more sense, but we try to solve for as many reactions as we can when it's all together. Then what we're going to do is we're going to break our frames into their individual members, okay? And then we're going to include any applied loads, all reactions at the supports. We're also going to be looking at internal pin reactions, and those are going to get pin reactions, X's and Y's. And then when we're moving from member to member, so we'll solve for one member, then we'll look at another member. And as we do that to the next, we are going to change the direction of the force. Okay, and then again, that will make a little bit more sense when we do these problems. And then you'll notice here, letter D here says that we're going to use the equations of equilibrium to solve for any unknown variables. Now, when we get to our last member, we will know that we did okay because, and that we did everything correctly because we'll notice, just like we did for trusses, that all the forces will equal zero. So it'll all balance out. And if we don't, then we know along the way somewhere we missed something or we miscalculated. Okay, so let's take a peek at our first example. And our first example problem is going to be on page 122 in that handout. So I am going to kind of get to that page and I'll pull it up underneath our camera here. So on page 122, example 6-7 starts halfway down the page. Okay. So we have a frame and it is shown on figure 627, which happens to be on the following page. So this is the frame, kind of the overall view of what we're going to be looking at. I'm going to kind of ignore the other views that we see here. Okay. And what we're going to do is we are going to solve for all of the pin reactions that are internal to our frame. Okay, so you'll notice that we have a frame member right here, and we're going to refer to that as A, B, C. So this is a continuous frame member. Another continuous frame member from C to D to E. And then we have one cross member here, B to D. You'll notice that we have a weight of 600 pounds mid-span on this particular member. And then we have another one, 1,000 pounds. These two loads are not at the joints. That's what the difference between a truss and a frame member is, okay? And then you're going to notice at the two supports, A and E, we've got a pin connection and we have a roller, okay? So we're going to use that process that we just referred to go through and solve for all of the pin reactions at C, B, and D, and then also the reactions at the supports for this frame as we see it supported here. Okay. Now, yeah, I know that you just came in. We're on page 123 in our chapter 6 handout that's in module 6. Okay. And we're working on the frames and the machines guided notes. All right. So now what we're going to do is as we look here, we're going to first draw the free body diagram of the entire frame together. Okay. Now, in the past, our free body diagram, we have, drawn or simplified with just lines to show members, okay? But we do need to show that C, B, and A are a continuous member as well as C, D, and E. If we just do a line and not have thickness to the members, it's going to be hard to tell that there is a continuous member. So I'll kind of show you how we're going to represent that. So drawing the free body diagram of the entire frame together, I'm going to start with the vertical member here, and I'm going to give it some thickness, okay? So C is going to be at the top, so I'm going to show that, kind of what we see here. So this is going to be our point C. B is a little bit lower than center, so I'm going to go there with B. And I'll probably show it like this. And then A is down at the bottom here, okay? And then I'm going to kind of do the same thing where I have that member C, D, and E. See, C, D, and E is going to be a little bit higher than A. So this is going to be point E. And then D is going to be straight across. And then C connects. And then we're just going to show member B to D here. And again, I do want to show the thickness here so that we can see that this is a continuous member, this is a continuous member, and we have the member in between. Okay. Now, A and E, we'll look back at the diagram. A and E are our supports. So A you can see is a pin and E is a roller. So that means that we are going to represent the reactions there. So since A is a pin, I'm just going to draw an X and a Y reaction at A. Okay, and I'm just going to show a y going up and a x going to the right. Okay. And then E is a roller. Since that roller is riding on a horizontal surface, our reaction is going to be perpendicular to that. So this is going to be EY right there. All right. Now we have two loads, as we saw. We have a 600 pounds going down mid-span on BD, and we have 1,000 pounds going to the right, 4 feet down from point C. Okay. So I'm going to show 1,000 pounds here. Okay. And then 4 feet here, 4 feet here, and then 5 feet there. And then over here, coming down at mid-span, I have 600 pounds, 600 pounds. And then you're going to notice that I have 3 feet in between here and 3 feet there. I should have made my diagram bigger. I always say that I'm going to do that, but I got caught here. So 3 feet in between each one of these spots here. Okay. Then we want to show the dimension to E between A and E. So that's going to be, it looks like 9 feet. And let's see if I can get this in here as a dimension like this. There we go. So this is 9 feet. And although they have the distances, the 10 and the 5 along here, I don't believe, if I remember correctly, that we need those. But what I do need is I need that in this illustration right here, notice there is a 1 foot distance, a height between where A is and where E is. We do need that dimension. So I am going to draw a little dimension right here. And this is going to be 1 foot. Okay. And that should be everything that we need as far as our free body diagram of our entire frame together. Okay. Any questions at the moment on generating that free body diagram? I pulled out the chat box, so feel free to put it in there or audibly ask. Okay. So if there aren't, then our job number 1 is to calculate the reactions at our supports, which are A and E. Okay, A and E. So notice that we have an AX, an AY, and then an EY. So tell me, what do we want to do first to calculate at least one of those values? Anyone? No suggestions? This might take a while to get through our lecture tonight. What do we want to do to try to solve for those reactions? We have 3 equations of equilibrium, right? Which one do we want to start with? Sum the forces in the X. Yes, let's do that. And as I'm getting started here, I almost forgot. I'm going to be using my convention to determine my positives and negatives. Yes, so let's sum our forces in the X direction equal to 0. Remember, it's identifying that we are in that mode of equilibrium. So as I look here and I look at my X forces, anything that's horizontal, I have a positive 1,000. And then make sure you put your units in. And I've got a positive AX. Those are the only 2 forces in the X direction, so I can set those equal to 0. And now I'm going to move my 1,000 to the other side. So AX is going to be equal to a negative 1,000 pounds. Okay. Well, as we know, that's a little bit of a problem. So we can never leave a negative as a final answer because what this says is you assumed the wrong direction. Okay. So what I'm going to do is 2-part process to correct this. I'm going to make this a positive value because I never leave it as a negative. And then I'm going to go up and I'm going to change the direction of AX. Okay. So it has to go to the left. And that makes sense because if I am in equilibrium, that means everything balances. So if my 1000 is going to the right, that means that my AX, the only other force going in the X direction, has to go to the left. Okay, so that's okay. So now I can put a box around that because that is one of my reactions. Okay, and I can say equal to 1000 pounds. All right. Now what do I want to do? I've got two more equations of equilibrium I can use. Sum the forces in the y, sure. So let's see what we can do there. So I'm going to sum my forces in the y equals 0. Make sure you tell me you're going to do that, okay? And now we're going to look at our vertical forces. So we have an AY going up. We have 1000, or I'm sorry, 600 going down. So that'll be a negative. And then we have a positive EY, okay? Those are all of the forces in the y direction. I'm going to set that equal to 0. I'm going to put this 600 on the other side, but I'm left with two unknowns. So that just means I can't really go any further. So we're gonna leave that there. And as we've seen in the past, we'll probably be able to come back and fill that in. So I do have one more equation of equilibrium, right? Sum the moments. Yes. Oh, and Lacey already said, let's go around A. I think that's a great idea and great choice because our two unknowns are AY and EY. So we're going to want to either go at A or at E to eliminate that one to solve for the other one. So yeah, let's do the moments around A as Lacey suggested and then solve for what's going to be the reaction at E. So I'm going to leave a little room because I know I'm going to be adding here. So I'm going to sum my moments around A equal to 0. Okay. And so I'm going to put my finger on A. And you know what? You guys are getting to be experts here. So I am going to let you write your equation and then we can compare and then solve for EY. So I'm not going to talk it through this time. I'm going to do it here in the background, but I want you to do it as well. So you should end up with EY equal to 1,200 pounds. Okay. EY is equal to 1,200 pounds. So with that, since now we know what EY is, we can go back up to our sum of the forces in the Y direction and use that 1,200 here to solve for AY. Okay. So I'm going to do that. I'm going to plug that in. And you'll notice what happens. When we put our 1,200 to the other side, it's going to be 600 minus 1,200, right? If I go like this. And I end up with negative 600. So what that means is I assumed the wrong direction for AY. Okay, so we're going to go up here. We're going to make this a positive value because we never leave any of our answers as negative. But we also have to then follow up with putting the arrow on AY going down. Okay, so AY is going down, and then we can put our box around AY. Okay, so AY is going down 600 pounds. So I'm going to put 600 pounds below here. EY is going up and it is 1,200 pounds. And AX is going to the left and it's 1,000 pounds. Okay. Any questions on the results that we have so far? So this is our first step, drawing the free body diagram of the entire frame together and solving for the reactions at the supports A and E here. Okay, and we were able to solve for all of them, which is good. Now, the other part of this problem is they want us to find out what are the reactions at each one of the internal pins to this frame. So we want to find out what's the pin reaction at C, at B, and at D. Okay, so to do that, we need to break our frame apart piece by piece. And this is where we're going to be looking, for instance, at A, B, C by itself, okay? And then C, D, E by itself, and then B, D by itself. So if we turn the page, I believe it has us starting with that vertical member. Yep. So it says, draw the free body diagram of member ABC to determine the reactions at those internal pin reaction or pin connections. Okay, so that's what we're going to do. We are simply going to draw our vertical member. Now, in this case, because we're just worrying about the single member, you don't have to show it with thickness. It's when it's together so we can see that it's a continuous member is where it's important. So I'm just going to show this as a simple line, and C is going to be on top, and then I've got B, and I've got A, okay? Now, here's where we got to kind of distinguish between external loads and then these internal pin reactions. So when our frame is completely together, notice that we have 1,600 and the reactions at the supports. Those are what we call external loads. They're external to the entire frame. The pins here at C, B, and D, those are internally keeping everything together. So any external loads that we have, the 1,000, the 600, and the reactions at the supports are going to stay in their same orientation, okay? Same orientation. So I'm going to put those on first. I know that I have 1,000 pounds going to the right. And there's 4 feet here and 4 feet there. Okay. Then I have my AX and my AY. And remember, we changed their directions to go to the left and they're going to stay in those directions. So this is 1,000 pounds, which is AX. AY was going down and that was 600 pounds, 600 pounds. Okay. And then this is 5 feet. Okay. Those are the external loads, all right? The reactions and the applied load. Now what we want to do is we want to represent the pin reaction. So just like a pin reaction, a support, an internal pin is also going to have an X and a Y value. So at C here, we're just gonna assume a direction. So we're going to show this as CX. And we're going to show it as CY. And I just offset it from the line a little bit just so we could see it. Now, whether you show it up or down or left or right really doesn't matter, okay? I'm going to show my CX going to the right. I'm just randomly putting it on here, and I'm going to put my CY going down. No other reason than I'm just putting it on. That's it, all right? And I'm just kind of looking at the example in the book, and that's what they have, all right? We may change that direction. Remember, when we calculate our values, if we end up with a negative final answer, then we just know that we assumed the wrong direction and we need to put it opposite whatever we assumed, okay? Then we're going to do the same thing at B. This is also a pin reaction. I'm going to use those same directions, BX going to the right and BY going down. Okay. So now those are all the forces that are on this member. So we've got the reactions at the support, we've got the applied load, and then we've got the internal pin reactions. Okay, so now what we have is we have four unknowns. We have By, Bx, Cy, and Cx. So we want to see, can we solve for any of those? And we're going to use our equations of equilibrium to see how far we can get. Okay, so any ideas what we want to start with? We've got our three equations of equilibrium. Which one do we want to start with first? Start with the x. Okay, yes, let's do that. So we're going to sum our forces in the x direction equal to 0. So we've got a positive cx, positive 1,000. We've got a positive bx. Oopsie, maybe put a plus in front of there. Positive bx. And then we've got a negative 1,000. Okay. And those are all of our x forces. So we're going to set that equal to 0. Okay. Now, as we can see here, the 1,000s are going to cancel each other out, right? So we have Cx plus Bx is equal to 0, okay? And those are two unknowns, so that means that we can't solve it at this point. So we're just going to let that sit there. We're not afraid of that. We'll come back to it and we can fill it in. Any other ideas? What can we do next? Sure, we can do the y's. Yep, let's try the y's. Let's see what we do there. So I'm going to leave a little space here because I know I'm probably going to be coming back and filling that in. So I'm going to sum my forces in the y equals 0. And now I've got a negative cy, a negative by, and a negative 600 is equal to 0, right? So these are my 1, 2, 3 forces in the y. So I'm going to put my 600 on the side, or on the other side, we're going to have a negative cy minus by is equal to 600, oopsie, pounds. I got to put those in there. And again, we've got two unknowns, and that's okay, but we can't solve for anything there, right? So now what are we going to do? Some are moments, right? Now we can. Nia already said C, and Lacey said A. Either one of those, will be okay. But where we want to focus is where our unknowns are. So our unknowns are at C and at B. So C or B will help get rid of some of the unknowns. All right. If you go around A, we'll just end up with two unknowns, and then we would probably go to a different point. So let's go ahead and use some of the moments around C, like Nia had suggested, and then I think that'll be more helpful just because we'll be able to get rid of that one. So I'm going to leave a little space here. I'm going to sum my moments around C equals 0. And again, we're going to put our finger on C, so that eliminates Cx and Cy, and then we're going to move in the direction of our offset forces. So we've got 1,000 pounds times 4 feet. It is going to rotate positive. Then we've got Bx, that's going to also rotate positive, times 8 feet. And then I've got 1,000. And and I should say By is actually on the line pulling through. So there's no offset distance. So By is not included. And then I have my 1,000 at the bottom here. And then the total distance here is 8 plus 5. So that's going to be 13 feet. And it is going to pull in a negative direction. So negative out front. And that's going to be equal to 0. The 600 as well is pulling on the point, so it wouldn't be included. So our only unknown here now is Bx. So go ahead and solve for Bx.
Hey, Kelly, just to clarify, we don't have to put the convention in the top right, correct? Because we're using the convention from the
Yep.
original problem?
Well, yeah, because so we started the problem over here,
Yeah.
so you are correct. Then we just
Okay.
put it once for the entire problem. We're going to continue to use that. Thank you for asking. Yep.
Yeah, perfect. Thank you.
Mhm. Wait. Which this bx is equal to 1125. Okay. Oops. So you should get 1125 for bx. Notice it's a positive value. So that means the direction that we assumed was correct. Okay. So this is equal to 1125 pounds. Everybody get that value? And I did confirm it. It's the same thing as in the book. So now that we know bx, that means that we can plug it in up here to find cx. So let's go ahead and do that. So we have cx plus 1125 pounds is equal to 0. And then now we can solve for cx is equal to a negative 1125 pounds. So that just means that we need to change the direction of cx to go to the left. So we're going to make it positive here. Remember, we're not going to leave a negative final answer, but then the second part of this is we have to change the direction to go to the left. Okay? So cx goes to the left and it is 1125 pounds. Okay? So our moment around C did help us to find the X directions on here, but our Y's are still unknown. And that's okay. That's okay. Because now what we're going to do is we're going to move to the next member and maybe we can get some information there to help us out. Okay. So any questions so far? All right. So now we're going to draw the next member. And the next member that we're going to look at, and it could be either one, quite honestly, but the next one we're going to look at is going to be that horizontal member BD. Okay, BD. So we're going to draw the free body diagram of it. And it is simply a horizontal line. Okay. And the left side is B and the right side is D. All right. Mid-span, we have a 600-pound force going down. And it's 3 feet and 3 feet on either side. So a total 6 feet long. Now, this is where when we have internal pins, okay, when we have internal pins, if we go back to our first sheet here, you'll notice that in C where we added our little line here, when we move from one member to the next, we change the direction of the force, okay? And that's going to be for those internal pin reactions. So since we assumed and we confirmed that BX was going to the right on member ABC, we are now going to change the direction and it is going to go to the left on member BD. Okay, so this is going to be BX going to the left. Applied loads, external applied loads remain in the same direction, but these internal pins, they switch directions. So it was BX up here was going to the right, so it's going to go to the left down here. And this is equal to 1125 pounds. So same magnitude, opposite direction. Also, we assumed BY going down. Okay, so I'm going to move my B here again. We're going to show BY going up. We don't know its magnitude yet, but opposite direction on an internal pin. Okay. Then over on the right-hand side at D, I'm going to move D. Since we have BX going to the left, I'm going to show DX going to the right. Okay. And since we have 600 going down in the middle and BY was on that side, I'm going to show DY going up here. Okay. Because logic kind of tells us it's going to, support going up since this is mid-span in the middle going down. Okay. So now we're going to solve for the values that we don't know. So we want to find BY, DY, and DX and see how we do. Okay. So first things first, we have our 3 equations of equilibrium. Which one do we want to start with here? Sum the forces in the y. Yeah, let's go ahead and do the y's. So if we sum our forces in the y direction equal to 0, we've got a positive by, a minus 600 pounds, and a positive dy, right, equal to 0. We're going to move our 600 to the other side. By plus dy is equal to 600 pounds. Okay. Two unknowns there. That's okay. We have two other equations of equilibrium. What's the next one we want to try? Sure, let's do x, as Lacey said. Okay, I'm going to scooch down here. Sum my forces in the x direction equal to 0. I've got a negative 1125 at bx, and I've got a positive dy, right? Equal to 0. One unknown. This is a good, so I'm going to have, oopsie, dy is equal to 1125 pounds. Look at that. There we go. So that means, oh no, x. Wrong one. So sorry. 1125 pounds. This also came out as a positive number, so we assumed the correct directions, which we were pretty sure we were going to do, right? So 1125 for dx. All right, we have one more equation of equilibrium, right? And we have by and dy. Where do we want to sum our moment around? So we are going to sum our moment, but where are we going to sum it around? Should a little bit lower. B. I like B. Yep, that'll take out that one so that our other one will be available to us, or we'll be able to solve for it. So moment around B equal to 0. So go ahead and write your moment equation here. You should find that your dy comes out to 300, okay? And as we look, excuse me, you'll notice that since we have the 600 going down right in the middle, it does make sense that dy is going to be 300, and we can guess that our by is going to be 300 as well. But everybody get the 300 here? Okay. Just a note, just to kind of mention it, notice that I'm putting my units in all phases of the problem, canceling out when I need to, or combining as I go along. Make sure that you're doing that in the work that you hand in, because I will be looking for that, okay? That's part of the requirements in the formatting. Okay, so now that I know that dy is 300, I can put it up here, right? So this is going to be by plus 300 is equal to 600. And we're going to subtract it on both sides. So by is going to be equal to 300 pounds. And again, positive value. So, and it's going up. That means we assumed the correct direction. So both of those are 300. Now, what we want to do is, if you recall, up here, we needed a by, right? And since we determined the correct direction on this member was by going up and its magnitude is 300, when we go back up here, we have to make sure that it's in the opposite direction. And indeed it is. It is going down here, okay? So we know now that by is 300 pounds going down. So we can plug it in over here, okay? So we're going to have a negative cy minus 300 is equal to 600 pounds. That 300 is going to go to the other side, so we're going to have negative cy is equal to 900 pounds. Negative is not good, so, and it kind of makes sense. You know, we had these all going down, all right? The 600 was going down. We determined the 300 is going down. We have to have something going up, right? So cy is going to need to go up. So we're going to make it positive over here. We never leave a final answer as a negative. And then we're just going to erase the direction of cy, and we're going to change it to go up. So make sure it's up on this member, okay? Now, if we look back at our original put together, all together frame, we now have done CBA or ABC and BD. We need to go ahead and do member CD, okay? Or CDE, sorry. Okay, so that's going to be the next step that we have here, number 5. So we know, and I can again, because this is the only member that we're interested in, I'm just going to draw a line for this member. I'm going to identify my C up here, my D here, and then E is down here. Now, we want to put on first any external loads, okay? And remember, the support is an external load. These are internal pins, okay? So let's do our external load first, and those stay in the same direction. So I have my EY, and I know my EY was 1,200 pounds. So from here was 1,200 pounds. And this is the only force at E because it was a roller. So it was that just a roller that was perpendicular to the surface it was riding on. Okay. So 1,200 pounds there. And then now I want to add the forces of these internal pins. And I have to go back to the previous members to find out their values. So I'm going to start up here at C. C is up here. Now on member ABC, CX was going to the left. So that means that CX is going to go to the right this time, and it is going to be 1,125 pounds. So same magnitude, just opposite direction. Okay. So I can label this CX if you want. Okay. Then our Y direction, CY is going up on the other member. So that means it's going to go down on this member. Okay. So this is CY, and that value was 900 pounds. A little close there. Do this. There we go. Okay. Then we're going to go to D. D was this member down here. We had DX going to the right, 1125. So we're going to switch that direction. It's going to go to the left, 1125 pounds. Okay. And that's DX. And then our Y direction on that member was going up. It was 300 pounds. So it needs to go down. dy is equal to 300 pounds. Okay. Now, you'll notice that there isn't anything to solve for here. We know all these values. So when you get to your last member, just like with trusses, you should know everything. And the only check that you want to do here is that everything equals 0. So we're going to sum our forces in the X and Y and make sure that everything balances out. So if I sum my forces in the X direction equal to 0 here, I have a positive 1125. I have a negative 1125. Those are my only two forces in the X. They're going to be equal to 0. And sure enough, 0 equals 0. Okay, that is good. I'm going to do the same thing in the Y direction. So I'm going to sum my forces in the Y direction equal to 0. I've got a negative 900 at CX, negative 300, I'm sorry, at CY, negative 300 at DY, and a positive 1200 at E equal to 0. Sure enough, 0 equals 0. So what that tells me is when I ended up in equilibrium on my final member, that means that all of my values previous to this were all good and I did the problem correctly. Okay. If I end up and something is not equaling, I don't get my 0 is equal to 0, then I know I've got to go back and I've got to try to find where I made my mistake. Okay. So questions, frame members, similar. There's some similarities to trusses, but the main difference is that frames can have forces that are mid-span, where trusses, you could only apply forces at the joints. Okay. So if there aren't any questions on this example, what I'm going to do is I'm going to stop my recording here, and then we'll start the next example in a bit.